We've reached the halfway point of this class. And I think this is where it starts to get interesting, because rather than grinding away at the math, like the phasors that we just learned, we can start to look out and apply that math and that thought process to things in the outside world. For example, we can look at this three-phase power line and come to some understanding of how it works. We can also look at things like transformers. And that is the topic we're going to explore today. Transformers such as this one here, or the one hidden way back here. It's a rather short lecture today because all we're going to discuss is the ideal transformer. This structure is an iron core onto which we place several windings. We call this first winding the primary winding. We'll connect that up to an alternating current voltage source. And we will talk about the number of turns, which is quite literally the number of times the wire is wrapped around the iron core. We have a second set of windings on the other side. We call this the secondary winding. To this, we connect our load. And once again, we talk about the number of turns. It's important to recognize that these coils are magnetically coupled. You recall from our earlier discussions that there are flux lines that flow in a circle, and they will cut through both of the coils. It's important to recognize that this is an alternating current, which means the magnetic flux is always changing. For example, on the positive half of our sinusoid, the flux lines will be flowing in this direction. Later, on the negative part of our sinusoid, the flux lines will be flowing in this direction. So they're always changing in the core. Let's make a note of that. We should also mention the transformer is an alternating current device. We can sketch the schematic for the transformer. We start with the source. Here is our primary coil. We put 2 bars here. That's representative of the iron core. And then we have our secondary winding, and finally the load. We can talk about the turns ratio. For example, if this particular transformer had an input voltage of 120 volts, we could expect the output at the load here to be 240 volts. Here's a few must-know equations for your note card. So we talked about the turns ratio. And as you saw or implied here, the turns ratio is definitely related to the voltage ratio. In fact, we would say the voltage on the primary divided by the voltage on the secondary is equal to the number of turns on the primary over the number of turns on the secondary. Keep in mind that this was the primary winding and this was the secondary winding. Again, this here is the voltage ratio, and this is the turns ratio. So we have voltage, turns, and now we have the current ratio. And this one is completely upside down, where we have secondary on top and primary on the bottom. This is the current ratio. The other thing you need to know about a transformer, especially for the ideal transformer, is that there is no power loss. Now, we know this is fictional, because transformers, just like everything else in the world, have a power flow diagram. And if this is our power out, this is our power in, our power lost, we know that the efficiency will always be less than 100%. However, for now, we're assuming that there is no power loss. We say eta is equal to 100% in an ideal situation, or for an ideal component. Another way of saying that is that the complex power in the primary is equal to the complex power in the secondary. We can put these thoughts together in a quick example. Here we have 5 amps of current, and when we measure across this resistive load, we measure 90 volts RMS. Our turns ratio is known to be 3 to 1. We would like to know the current and the source voltage. From your note card, you know the voltage in the primary or the voltage in the secondary is equal to the number of turns in the primary over the number of turns in the secondary. So V primary is to 90 volts as 3 is to 1. If you do the cross multiplication on this, I think you'll find that the voltage on the primary is equal to 270. So that takes care of this piece here. From your note card, you also know that the turns ratio is equal to the current ratio, except it's upside down. So we could say 3 is to 1 as 5 is to the current in the primary. So now when we cross multiply, we end up with 3. Current in the primary is equal to 5. So the current in the primary is equal to 5 divided by 3, which is about 1.6 amps. So that goes here. It's 1.6 amps. We can check our work by calculating the power. Remember, power is equal to the current by the voltage. In this case, it's 5 times 90. So 5 times 90 gives us 450 watts. And then we try the same over here. We said power is equal to IE, which is 1.6 amps by 270 volts. So a bunch of 6's times 270 gives us the same 450 watts. So that gives us some confidence that we have worked out this problem correctly. Let's work another example, except this time we're going to put a twist on it. We're going to try to explore why we would need transformers in the first place. We'll let transformer 1 have a 1 to 10 ratio, and we'll let transformer 2 have a 10 to 1 ratio. We have a 5 kilowatt load, and that load must receive 120 volts. In this example, it's important to realize that this piece here represents wire. You could think of it this way. Suppose we have our house, and that house has a long wire headed off to an outbuilding, maybe a small workshop or something like that. Now, it's not just one wire, mind you, it's 2, because you have to have the wire there and you have to have the wire back. It's important to recognize that this wire has resistance, and that can be very important. So here at the house, for instance, we have 120 volts, And if there's no load, you're also going to have 120 volts in the outbuilding. However, if you put that heavy load onto the wire, the voltage will no longer be 120 volts here. It might drop down to 90 volts or less, and that can be quite a problem. To get around that, we look at the transformers. So here's that wire we mentioned, and we'll assume that wire has a 12 ohm resistance. And what we've done is we've sandwiched it between two transformers. This transformer is the step-up transformer. It takes the voltage and steps it up by a factor of 10. And this transformer is a step-down transformer because it knocks the voltage down by a factor of 10. Tell you what, let's use our math and see where that gets us. So if we wanted to know the current in the secondary of T2, we would say that is 5,000 over 120. That's just a statement of pi, right? So if you wanted to know the current, it's power divided by a voltage. So the current on the secondary of T2 is 41.6 amps. We can now move to this part here, and by inspection, because this is 120 volts and this is a step-down transformer, we can say that it stepped the voltage down by a factor of 10. So the voltage on the primary of T2 is equal to 1200 volts. We can calculate the current on the primary of T2 using this rule. So this is our turns ratio, and that is equal to our secondary current over the primary current of T2. Solving for that, the primary current of T2 is equal to 4.16 amps. So we see that what was 41.6 amps is now 4.16 amps. And what was 120 volts is now 1200 volts. So by stepping the voltage up, we've dropped the current by the same factor, which is a good deal for us because that means there will be less voltage drop across this wire. There'll also be less power lost in that wire. So we can talk about the voltage on the secondary of T1 is equal to 1200 plus 12 by 4.16 amps. Now keep in mind that there's a current here of 4.16 amps. And because we have this resistance, we can calculate the voltage drop on that. That's just an application of Ohm's law. So we can calculate the voltage drop across that resistor as a current times a resistance, and then we add it to the 1200 volts. Stated another way, we're just doing Kirchhoff's voltage law in there. So the voltage on the secondary of T1 is equal to 1250 volts. And finally, we're at our source. And we can say the voltage on the primary of T1 is equal to 125 volts. And our current is 41.6 amps. So if we look at this start to finish, we talk about 125 volts here. We end up with 120 volts on this side, and we started out with 41.6 amps, and we ended up with 41.6 amps over here as well. We used a step-up transformer here to boost the voltage up to about 1200 volts and run it across the wire, and then we used a step-down transformer very close to the load to bring that voltage back down. And the reason we did that was to minimize the power lost on the resistor. That power loss can be calculated as I squared R. So we said the current was equal to 4.16 squared by a resistance of 12. So that is 4.16 times 4.16 times 12. So in this case, we're losing about 200 watts of power. We can think about this with the power flow diagram. We lost 200 watts in the wire. We had 5 kW out here, which means we must have had 5.2 kW going in. Keep in mind that this was for ideal transformers. Real transformers will have more loss. Suppose we tried to do this without the transformer. Let's do a calculation where we still have to get 5 kW with 120 volts to our load, and we still have the 12 ohm wire, but this time we don't have the transformers in the circuit. So we end up with something that looks like this. We have our unknown voltage source, a 12 ohm wire. We still have to get 5 kW out here, and we have to have 120 volts as measured at the load. Our current hasn't changed. Our current is still a power divided by a voltage, which I believe was 41.6 amps. But now watch what happens here. If we use Ohm's law, we say that the voltage is going to be 120 volts, because we need 120 volts out here, plus the voltage drop in that resistor, which would be a current, so 41.6 by our resistance, by 12. So the voltage as measured at the generator, right? In fact, maybe we should change this. So we'll call that the source voltage. So Vs is equal to 41.6 times 12 plus 120. So we need about 620 volts out there. Okay, well that's not good. That's rather inconvenient. But let's see what happens to the power loss. So power is equal to I squared R. So power is equal to 41.6 squared by 12. So what is that? 41.6 times 41.6 times 12. So now we see our power loss is about 21 kW, which is an extraordinary statement when you think about it. In order to feed the same 5 kW load, we lost 21 kW in the wire. The wire itself got hot, which means we need to put in about 26 kW. So here you put in 5.2 kW. Here you had to put in 26 kW, with all of that extra energy lost in the wire. With that thought in mind, we end up full circle, back to where we started. If somebody asks you what is the purpose of a transformer, you look at a power line and you say, do you notice? Do you notice the insulators? Those are awful large insulators, which implies that the voltage on the transmission line must be very high. So what you do is you put a transformer at either end of the transmission line. You boost up the voltage, which means you lower the current, which reduces the amount of I squared R loss in the power line. You could say that transformers are the one piece of enabling technology that makes our power grid operate. If we didn't have transformers, these wires would be huge. They would be so thick that we couldn't afford to run them. But with the transformers, the wires can be made small because the currents can be made low, with the voltages being high.